Welcome back, everybody, to the graduate school. And in particular, welcome to those of you who are joining us online. Feel free to ask questions at any time. Hi, Kumar. Good to see you. Okay, so it's a great pleasure to reintroduce Stephen Amelotte, giving a series of brilliant talks on polyhedral products. Thank you, Stephen.
Thanks very much. So the plan today was to get to some, last time we talked about lots of connections between polyhedral products and commutative algebra, and the plan for today was to look at some connections to geometric group theory or polyhedral product models of classifying spaces anyway. But there was something to finish up with the stable splitting. So we saw this Hochster formula last time, and then we said in words, and Tony remarked about it, that it's even an isomorphism of rings, but I don't think I actually wrote down the ring structure on the right-hand side. So here it is. You can understand the ring structure and cohomology, any coefficients here, in terms of the combinatorics of like the full subcomplexes of K, by looking at these exact maps like this. Notice there's a shift, A and B to AB minus 1. That's coming from the fact that we're taking this map to be induced by this sort of map of simplicial complexes, where the join is secretly, topologically, like it's a suspension of the smash, right? So that suspension accounts for this shift here. And I should say this is for IJ disjoint and 0 otherwise. So the ring structure, you only have cup products coming from like disjoint pieces, this Hochster formula here. So if you take your K to be triangulation of some space that has cup products, we said that like the cohomology groups, that space you triangulate, take as your K, will show up in the cohomology groups of ZK, but the ring structure, cohomology of K, isn't really showing up. It's a little different. Okay, and then we said that one of the good things about the BBCG splitting is that this was some like celebrated classical result in commutative algebra that's recovered by it. So let me remind you where we stopped there. The BBCG splitting really only gave like the general form, which looked something like this: the suspension, any polyhedral product splits is a big wedge indexed by all the subsets or vertex set, and the summons just look like suspensions of some polyhedral smash products, which we denoted like this. So the polyhedral smashes associated to each like full subcomplex of K. And then I said that like the real interesting part about the splitting is in identifying these summons more explicitly in various cases of interest. So let me try to go through some of that quickly. So put it all inside of this theorem statement. Moreover, in case the inclusion, our cofibrations like AI going into XI are all null homotopic. So suppose that happens for all I in our sequences of spaces here. Then they identify these suspensions these polyhedral smash products as follows. So each one is going to split up even further as a wedge. Now we're going to index over all the faces present in this full subcomplex, so sigma and Ki, and we'll have the suspension of the geometric realization of the link of sigma. And that is then joined with a smash of X's and A's. Right, so these were like the ingredient spaces in the definition of the polyhedral smash. So this thing for any sigma is just like an I-fold smash of xi's and ai's, where as usual, sigma tells you in what factor you put an xi and what factor you put an ai. And I should tell you just in general what the link of a face in any simplicial complex is. General definition is just like all of those faces tau in K that are disjoint from sigma, but have the property that sigma union tau is a face of K. So an example is if you're looking at like a sphere triangulation, it's your simplicial complex K, and you pick a face to be a vertex. Say locally, we're looking at like a two-sphere triangulation. So we're going to see a bunch of triangles coming in at any vertex V, right? So the link would just be all those faces of K that are disjoint from my vertex here with the property that adding them to the tau gives you a face, right? So that would give you like this, and this, and this, and this, and this. So in general, if you have like an n-sphere triangulation, the link of a vertex is then an n-1 sphere triangulation. It's just one example, but the only ones that'll be relevant for us really, the link of the empty face, so you can check from the definition here, will always just be all of K. Or if you took a maximal face, so I'm thinking if K is simplex on m-1 vertices, it has the maximal face present, right? And the set 1 through m is a face of that simplicial complex. And the link of that would just be the empty face. It's the smallest face to the biggest one and vice versa. I think that's all we need to know really about links. And we can notice that this happens in most of the examples we've been looking at. Like we've spent most time looking at moment angle complexes and Davis-Januszkiewicz spaces. In one case, all the A's were just a point, and in the other case, all the X's were cones, so they're contractible. So that would make these maps all null, right? Let's maybe look at this case first, where every AI is contractible, the Davis-Januszkiewicz case. So here, we can be more precise about each of these stable summons, because this space here, notice, whenever there's just a point involved in one of these smash products, that whole term is just going to become contractible. Smashing with a point gives you a point. So the only things that are going to survive in this wedge, just sitting inside of this bigger wedge, are cases when sigma is just maximal, right? It's like the entire vertex set, K sub I. So this hat thing is null except sigma is like the entire simplicial complex, K sub I, but that can only happen if K sub I is a simplex. So like a simplex on the vertex at I, which is an I-1 dimensional simplex. Right, so that gives us the following. Each of these suspensions here, or okay, each of these are going to look as follows. Contractible if Ki is anything other than a full simplex. And what's going to happen in case ki is a simplex and sigma is just the whole, maximal face, then this is just a smash of xi's, no ai's present. And what's happening over here? Well, this is the maximal face in a simplex. So we said in that case, the link becomes the empty set. So that might make you think that, okay, this term is also going to disappear. But what is the geometric realization of the empty simplicial complex? That's the empty space, empty set, thought of as a space. But then what's the suspension of the empty space? I think of suspension as a homotopy pushout, right? So homotopy pushout of empty set is one of this form. Pushout where you just collapse 2 points. So pushout is telling me to take these 2 disjoint points and like glue them along the empty set. So it just gives me 2 disjoint points. So really what you're getting here after suspending is an S0, not an empty space. And then S0 join this. That's just like a single suspension. Join being the suspension of the smash. Okay, so altogether, I think that gave us 1 suspension in front of this thing, which we said was just a wedge or a smash of xi's, which I'm writing x underline, I guess like smash capital I, right? All the relevant xi's. Okay, so putting all of that together, right? This was just an analysis of each stable summoned here. So altogether, this case where all the A's are contractible gives us suspension of the ordinary polyhedral product, x comma star. Looks like this wedge. The faces of K, the relevant ones. We just have these suspensions of smashes of X. So that's the overall splitting in that case. So like the Davis-Januszkiewicz space stably splits in this form, which is maybe not so surprising. And then the more interesting polyhedral products came when your A's weren't points, they're like actual subsets of the X's, as in a moment angle complex. And something sort of opposite is going to happen there. So now if we assume the xi's are contractible, what happens? Okay, so we don't want this smash to contain any x's, so that'll make everything contractible. So the only relevant pieces of this wedge are the ones where you only have a's there, but that only happens when this face is like the empty face. So when a vertex is contained in sigma, you put an x somewhere. Am I saying that right? Yeah, I think so. Sigma, we want it empty. So now x, a, smash, sigma, those are all going to vanish except and sigma is the empty face. So that gives us what? Each of these K sub i's will get the following. So like the link of the empty face, we said is all of K. So this link will turn into just the geometric realization of a full subcomplex. So suspension of geometric realization of K sub I. And then our join is just looking like a bunch of A's. So I'm writing that A smash I, right? Okay, and let me rewrite my join as a suspension of a smash. So I'll get one more suspension. I'll put a smash here instead. So sigma 2 of this ki, smash a bunch of a's. Okay, so now putting all that together in the same way, going back to the ordinary, on the top left. Like a wedge over all the subsets of M of these things. But notice that instead of writing all subsets of M, whenever I is a face of K, what does the full subcomplex look like? If I is actually not just any subset of our vertex set, but an actual face of K, what's the like induced subcomplex looking like? Yeah, it's just a simplex whose geometric realization is contractible. So it's only like the non-faces of K that are going to show up. And I'm just writing this now. Okay, I think I have all that right. So that's the final answer in this case. So this is what like a moment angle complex, for example, looks like stably, which is good. We had our very like abstract looking general splitting, now looking like something we can read off from K. Okay, maybe I'll just finish this little part with that example. So moment angle complex, just a D2S1 polyhedral product. We get stable splitting after just a single suspension, wedging over the non-faces of K. I have a double suspension of every full subcomplex. And then this is just an I-fold smash of, in this case, S1s. Smashing with S1 just means suspending even further. So I'll have like an I+2 suspension right here. And that's it. So everything disappears except for full subcomplexes of K. So now you can see why Hochster's formula is recovered as like a very special case of this general stable splitting. So corollary, just take homology to this splitting here, and we get the Hochster sum. Sorry. Our sum over here was over all subsets of the vertex set, but same thing. Notice that whenever J there is a face of K, that sum isn't actually contributing anything to the left-hand side because you're just looking at the reduced cohomology of a contractible simplex. So there, the same thing. And the other thing I wanted to say about that was that all of these suspensions we kept track of here, they just perfectly account for the shifting that goes on here. So we said yesterday that although we have like a graded ring isomorphism, it's not like Hn of this space is a direct sum of the Hns of all these full subcomplexes. There is some shifting going on where degree shifts worked in such a way that like the pth cohomology of any full subcomplex, HP, K sub I, really was contributing to like the P plus I plus 1 degree cohomology of the moment angle complex. So that looks right? Notice we have I plus 1 more suspensions over here than we do over there. Any other questions before, like I said, we shift to classifying spaces? Mm-hmm.
No, I have one.
No, he just liked the microphone.
Sorry.
Yesterday, you mentioned this intriguing fact that the splitting also gives you the multiplicative structure. From this presentation, can you say a bit more about where we get the multiplication, the cup product?
In like the general case, as opposed to the moment angle case? Because in the moment angle case, yeah, I can remind you that it comes from this Baskakov product. This is a ring isomorphism where we just look at inclusions of certain full subcomplexes and they induce the right maps to give us the cup product. But I also mentioned that something more general is true. Ari, Madirsky, Cohen, and Gittler also generalize this to get like a ring isomorphism between the cohomology ring of the polyhedral product on the left-hand side without a suspension and a direct sum of everything on the right-hand side without a suspension with a similar sort of formula called the star product. Yeah, so I won't write down the more general thing, but a similar field, yeah.
Just to make a cup product, you need to have classes. And right there, you've got a big problem. What are classes? And there is a theorem. It's a theorem called, which I'm sure Stephen doesn't have time to talk about. There's a theorem called the wedge lemma. And the wedge lemma allows you to, on a variety of theorems, allows you to actually write down names for classes. Cohomology of X, the cohomology of A, and classes which involve links, right? So you can actually give a name for a class. Take this class, and what happens when we multiply? Well, that is a very complicated question because when you multiply two classes, it upsets the combinatorics. So you have to have a way of multiplying the links. So that's the whole concept of product structure in the general cases. So it's very complicated, but doable. And wedge lemma allows you to name classes, and that's a big deal. Versus the Brazil resolution. In that case, you can name classes. You can go into the first and say, this is this many U's and B's, and I want to multiply that. But in the general case, you have to have a more sophisticated way of doing it.
Yeah, and this wedge lemma Tony is talking about is also what gives us this first thing that got all of this going, right? Allowing us to identify certain stable summons to look like that.
Anybody else like to ask a question, please? Are there any questions? Would anybody online like to ask a question, Stephen? Okay, thanks, Stephen.
Okay, yeah, like I said, there's going to be a bit of a shift now, but it's good to have this fresh in our mind anyway, because this Hochster formula and these stable splittings will show us how to understand group cohomology, certain groups in terms of Hochster sums like this. Okay, so usual setup, K will be a simplicial complex on M. I want to start category of groups. So let like G underline be just a sequence of groups, as many of them as we have vertices in our simplicial complex. And I'll also write things like B of G underline to mean the obvious sequence of classifying spaces, like space BG1, BGM, And just recall EG, BG are the names of these spaces in the universal principal G bundle. And we can think of G as being a subspace of EG, because the definition of EG is just a contractible space on which G acts freely. So we can just take like the orbit of the base point under the G action, that free action, and think of that as your G. So that's one pair. I'm going to consider some polyhedral products on EG comma G. And the other one will be like BG comma a point, just like the Davis-Januszkiewicz space. After the first day of lectures, someone here essentially guessed very early on, after we saw like the fundamental vibration in toric topology, that you might be able to replace S1 by any group and get a different sort of fundamental vibration, where the role of a torus is replaced by just any group you like, and you could try to sort of generalize all of toric topology by replacing a torus with any group at all. And that's exactly right. It turns out that there exist vibrations of the form EG comma G, that polyhedral product mapping into BG comma star to the K. And then this is just an inclusion into the full product of classifying spaces, just like with Davis-Januszkiewicz. So I'll move this up in a second so you can see it, but taking all of our G's to be S1 gives fundamental vibration, as we called it. Taking all of your G's to be Z mod 2 gave you the real analog. The real analog being the one where you have like real moment angle complex mapping to a real Davis-Januszkiewicz space, and then the classifying space is like Z mod 2 to the M. And maybe one other example, actually worth giving a name to for now, is if we take all of the G's to be Z, that corresponds to okay, EZ is like just R. So that's a weird polyhedral product to think about, but then B, the integers, it's just S1. So that's a much simpler polyhedral product to think about, because it's just sitting inside of an M-fold product of S1. So that's just a torus. So this is just a very classical way of allowing a simplicial complex to carve out a subspace of the torus. Just TM, right? No BTM. It's really a product of BZs. And this space is called the Salvetti complex. Okay. Okay, with those definitions. So here's a construction you can do with any groups that feels a lot like a polyhedral product. Graph products, groups. So let gamma be graph on our vertex set M. And actually, I now think I want to take my sequence of groups to all be discrete, say. I don't need that for the existence of this kind of vibration, and I won't need it for several things I write down, but eventually I will. Okay, then the graph product of a bunch of groups associated to a graph is written G to the gamma, and it's just the free product of all of your groups. G1. Maybe I should write like stars since we've been seeing a lot of joins in like 2 different contexts already. So take the free product and then mod out by some commutators wherever you have an edge in your graph. So like Gi, Gj equals Gj, Gi. If Ij is an edge that's present in your graph. And that would hold for all Gi and big Gi and all Gj and big Gj. I hope that's more or less clear from the notation. So the most important examples are called certain right-angled reflection groups. First, if we just take all of our groups G to be the integers, and let's take Gi to be a generator for each I. Then this construction defines what's called the right-angled Carleton group, or RAG. Associated to our graph. And it's usually denoted like A sub gamma. Looking at this definition, we can just give a very simple presentation of it, right? It's just going to look like M generators. The only relations between these generators are certain commutators. Gi bracket Gj will be the identity for edges Ij. Okay, maybe you've seen that group before, or at least heard of it. And then the other one is called a right-angled Coxeter group. Very similar, but take all of the G's to be Z mod 2s instead of Z's. Yeah, if each Gi, sorry, is Z mod 2, same thing, name some generators Gi, and the right-angled Coxeter group. Or ACG, I'll denote that W gamma. I don't know why people call it W. But it also has a very simple presentation. It'll look exactly like this, except all of our generators now are squaring to the identity. Okay, G1, Gm. Oh, sorry. So let's keep those 2 examples in mind, but back to the general case, notice that this G gamma, the graph product of a bunch of groups, it just interpolates between the free product of groups and like the direct product of groups, the ordinary product. Much like the polyhedral product, interpolated between like a coproduct and a product in the category of spaces. So notice this graph product interpolates free product of groups and direct product. So we have, for any graph gamma, some group homomorphisms, it's free product mapping into G gamma. Right, you get this for the minimal like graph on our vertex at M, namely no edges present, so no commutators present. Or if you take like the maximal graph on our vertex at the complete graph, that's corresponding to this product of the GIs. So like I said, this should remind you of some maps in spaces, say of polyhedral products, BG comma a star. So we'd have like the wedge over here, BG1, wedge up to BGM, polyhedral product BG comma star. It's interpolating between these two spaces. Okay, so these aren't fibrations so far. Whenever I've written two arrows, I think they've been fibrations, but here these are just some group homomorphisms. These are just some inclusions of spaces. And pi1 of a wedge gives us a free product. Or going the other way, we could get this group with the functor B. That would give us a wedge of classifying spaces. Same thing at this end, right? Pi1 of an ordinary product of spaces, just a direct product or direct sum in this case of the pi1s. And the classifying space of a product of groups becomes a product of classifying spaces. So what about the middle, right? This should suggest that maybe this polyhedral product, sorry, I don't know why I put a star here. This should just be like a K, right? We raise a pair of spaces to some simplicial complex. Is this a classifying space for this graph product? So is the polyhedral product of this form looks like it should be, but what K do you take? That's my next question, right? If the answer to this is yes, then like what K do we take? So you're suggesting we take K just to be gamma. We can do that. We can think of a simplicial complex as a graph, or vice versa. We can think of a graph as a one-dimensional simplicial complex. You could do that. I think that's a natural guess. That's what I would guess. Turns out to be the wrong thing to do. Well, I shouldn't say that. That's a good suggestion because that'll make this arrow happen. But if I just take K to be a graph, the space usually won't be aspherical, it turns out. So the only other natural thing to do, I think, instead of taking the smallest simplicial complex that has gamma as its one skeleton, maybe the biggest simplicial complex. So definition. Simplicial complex K is called flag. If it has the property that, there's a few ways to say this, but let me just give two of them. If like every set of pairwise connected vertices is a face of K. So whenever you find a bunch of vertices that are all pairwise connected by edges, the whole set will be a face of K. Another way to say that is just that K is flag if K is the clique complex of its underlying graph. So if it's like one skeleton, K1 to gamma. Okay, there's no gamma in the definition, but you know, if it's one skeleton. Maybe examples, you know, the boundary of a two simplex. This is not flag, right? These three vertices are pairwise connected, but the interior is not present as a face. So this is not flag, but like next polygon, that is flag. Or this is not flag, but I could make it flag adding a two cell or this sort of three-dimensional, or sorry, I'm thinking of it as two-dimensional simplicial complex. That would be flag, right? The way of saying this is all of your minimal missing faces have size 2. So that's definitely the case here. Okay, so let's try to prove that this thing becomes the right classifying space when K is like the clique complex of our graph gamma, or the flagification, if you like, of gamma. I want to leave this up, so let me state it over here. Theorem, the survey paper in the Handbook of Homotopy Theory, I notice attributes this theorem to like 5 or 10 different groups of authors going back quite a way. So it seems it maybe showed up in a lot of different places independently. But let me just write C panel ray 2002. That's just one place I know it appears in the way that I want to state it. So I won't assume K is flag right away. Let's just say K is any simplicial complex on M. And let's just call gamma the underlying graph, the one skeleton of K. And this is where I'm going to want to assume that my sequence of groups are actually discrete. Okay. Then first of all, for any simplicial complex with this underlying graph, we have fundamental group of the polyhedral product.
The camera is stuck. Oh, okay.
Okay, so I should avoid that side, right?
No, it's okay.
Could you say that again?
The camera was stuck for a moment on the right panel. Now it's okay.
Okay, let me know if I move somewhere you can't see, and I'll try to stick to these 4 boards. So remember this thing on the right. It's a graph product of groups. And then part B is going to say, we have this fundamental group, but it'll be aspherical. We'll have no higher homotopy groups precisely when K is flag. So let me phrase that. B, yeah, polyhedral product, EG to the K, is aspherical, if and only if K is flag. Right, so in which case, we will also have this arrow here. Sorry, I probably shouldn't write over there anymore. So in which case, a polyhedral product is B of something. Classifying space of this graph product. So I think there's probably lots to say about connections between polyhedral products and geometric group theory or classifying spaces, but this theorem is sort of the fundamental connection between these topics. So before the break, I thought this is maybe something good to prove, because aside from one very non-trivial step that I'll use, a fact about polyhedral products over flag complexes, mostly everything just uses some basic topology that I think any grad student knows. For example, part A can be proved using Van Kampen, and everyone knows Van Kampen. So yeah, let's try to sketch a proof in the next 10 minutes or so. The proof of A could go like this. We could try to induct K by adding simplices one at a time, building up a simplicial complex, right? Because we kind of just know for the smallest simplicial complex on a given vertex set M, namely the discrete simplicial complex, which is just M disjoint points, we have this identity which agrees with the graph product of the discrete graph. So that's sort of our base case, the idea to effectively add simplices to K. Okay, so if K is just M points, everything works out. We have the right fundamental group, right? We're just proving part A for now. That's just the left side of that diagram over there. Fundamental group of a wedge is a free product. Hopefully that's familiar. And then we could think of starting to add edges. So now assume K prime is obtained from K by adding an edge. Add a face like this. Then what does our polyhedral product look like? E.g., comma, a point raised to K prime. If you think of the definition of a polyhedral product as a union indexed by all the faces of K, well, we've only got one more piece of the union, right? The one associated to this new face. So we're just going to have whatever polyhedral product we had before adding an edge. And I'm taking the union. This union is really going to be over BGI wedge BGJ. And the new piece of the polyhedral product in this union, right, is just supposed to be an M-fold product of points or BGs. Put in a BGI, one place in BGJ in the other place. So a bunch of points, and we've got a So it's really just a copy of BGI cross BGJ. So that's something you can apply Van Kampen to, right? If we inductively assume fundamental group of this is the graph product of K, we can just see what Van Kampen does to add things here. Okay, maybe I'll just be quick and not write out the details. Van Kampen theorem leads to phi 1 of this new polyhedral product, K prime. It's just what you had before, but you add a relation coming from this new edge. So I guess you have to actually look at the relevant push out here in the Van Kampen theorem, and you can just compute that you've got this new relation gi gj equal to gj I for gi and gi, gj and gj. So that's our graph product for like gamma prime, right? Gamma prime being the one skeleton of this new simplicial complex K prime. Okay, and that's the hardest part, this little computation using the Van Kampen theorem. And then you just have to iterate this, right? You add more and more edges and the same thing happens. That just corresponds to introducing the right relations, giving you the right fundamental group. Part A here. But then who knows what K is, right? You might have to add lots of higher dimensional cells. And there you just argue that adding cells, I should say like faces or simplices, right? To my simplicial complex of dimension like 2 or greater. Well, this doesn't affect the right-hand side, right? Gamma doesn't care about K, it's just the one skeleton. Doesn't change the graph product. Right-hand side. And you can argue that topologically, adding cells of dimension 2 or higher, if you just think of the definition of a polyhedral product and think what's going on in terms of cell complexes, topologically, this corresponds to adding cells of like dimension 3 and higher. So that does not affect the fundamental group of a space, right? If you have a space and you add like a 2 cell, that could kill things in pi 1, but when you're adding higher dimensional cells, that doesn't affect pi 1. So that also doesn't affect pi 1. Okay, so that's how part A goes. And let me just quickly sketch part B, and then we can break for now. So we now want to prove an if and only if. Let's start by assuming K is a flag complex. It's the unique flag complex whose underlying one skeleton is the graph gamma. And we already know about the fundamental group. So we just have to show that there are no higher homotopy groups, right? If K is flag, show this is aspherical. So assume K flag. And let me write K bar for like the vertex set of K, thought of as a simplicial complex. So let it be, just M discrete points. Just the vertex set K, thought of as a simplicial complex. Then the inclusion, this minimal simplicial complex on the vertex set M into K, this induces a map of polyhedral products. And the polyhedral product, B, G, comma, a point, just the like M discrete vertices, that is just the wedge. It's just inducing the inclusion of this wedge of these ingredient spaces into our polyhedral product, e.g. comma star to the k, whatever that is. I'll call that map I. And then this is where I'm going to use a non-trivial theorem I said, a result of Panov and Theriot tell us that when K is flag, these functorial maps admit retracts, or sorry, a section, I should say, after looping. So there's a theorem that says the loops of this map admits a section, by which I mean like a right homotopy inverse. So maybe you can see how we finish from here, right? This is a K pi 1, Eilenberg-MacLane space, and this retracts off of it. So it must also have no higher homotopy groups. Right, so this is aspherical since this clearly is. Okay, that's a quick proof of one direction. And then just quickly indicate how the other direction goes. Instead of assuming that some space is aspherical and trying to argue that the simplicial complex defining it is flag, let us just instead assume in the other direction that K is not flag and try to construct some higher homotopy groups on the left. So this direction, briefly, assuming K not flag, that just means it must have like a minimal non-face, which is not just cardinality 2, right? It must have a missing face, which isn't just an edge. So there must be like a missing triangle or a missing 3 simplex or something like that. Let's call it I, right? So non-face of K with cardinality, let's call that N, right? Is like I1 to IN, some set of vertices, with N bigger than 2. That's what it means to be not flag, if you think of this definition, right? Okay, so now let's just consider this fibration that we had at the beginning. Well, first, case of I is a full subcomplex of K, and there was an exercise on day 1 to show that polyhedral products in the full subcomplex K retract off the bigger polyhedral product. So BG to the K prime is going to be a retract of this bigger polyhedral product. In particular, all of its homotopy groups are like summons of the homotopy groups of this space. So now let's just work with the smaller thing, and we're trying to show that it has some higher homotopy groups, right? That it's not aspherical. How can I do this quickly? Okay, so notice that the full subcomplex, since I is a missing face, right, a minimal non-face, that just means it's like the boundary of a simplex. It's looking like boundary of an I minus 1 simplex with I minus 1 or N minus 1 being bigger than 1. So that's what I meant by a missing triangle or a missing 3 simplex, something like that. So suffices to show that this thing has some higher homotopy groups. Consider the fibration we had at the beginning, EG comma G to the KI, so boundary delta n minus 1, that mapped into BG comma a point. And then that mapped into the whole Cartesian product, the BGIs. So we're still trying to show that this has higher homotopy groups. Well, this is definitely aspherical, right? It's just a product of aspherical spaces, classifying spaces. So these two things basically have isomorphic higher homotopy groups. So suffice it to show that this thing has some higher homotopy groups. This thing we know is a fat wedge. This also came up in the first lecture when K is like the boundary of a simplex. So just a fat wedge of all of these classifying spaces. And we looked at this theorem of Porter that identified the fiber of the inclusion of a fat wedge into the product. And the fiber just looked like a big iterated join of loop spaces of your ingredient spaces. But the loops, BG, is just going to give us copies of G. That's just going to be, okay, an I-fold join of a bunch of omega BGs. G's, that's going to be like an I-fold smash. So I should put like an n-1 here, suspensions. Smashes of all of these things, but these were just discrete groups. So the smash products, a bunch of discrete spaces. There's another discrete space, right? Just a bunch of discrete points. But then we're suspending that n-1 times, where n-1 we know is bigger than 1. So that's going to give us at least a 2-sphere, which has lots of interesting higher homotopy groups. So there's maybe something to think about there. If you just take like a grid of points, that's what this looks like. If you smash the integers with itself or something, get a grid of points, and then you have to think of suspending that, right? Well, take this product with an interval, and perhaps the two ends, you're getting a bunch of copies of S1 or S2 and stuff showing up.
There's a slightly simplified version, which uses side effect.
Oh, use Van Kampen to understand the higher homotopy groups? Sure, yeah.
Basically, it's the same.
Yeah, so either way, we can say that this fiber definitely has higher homotopy groups, and therefore this does, so it's not aspherical, right? So we proved K not flag implies our polyhedral product not aspherical.
Yeah, but just sorry to be repeated, but in order for that to be, if a non-lead, that G groups have to be non-trivial, right? So otherwise it may be.
Oh, good point, yeah. Just at least one of them non-trivial, or all of them non-trivial, I guess?
I think all of them, because
Yeah.
smashed, at least one of them.
Thank you very much. Non-trivial discrete groups. Okay, we should definitely stop there, but I'll answer any questions, of course.
Thank you, Steve. Anybody like to ask?